Welcome viewers. In this video, we are going to look the part 2 load calculation for design of warehouse structures. So in this video, the load calculations are as per European code. The following are the load details which we are going to look into this video: dead load, imposed load, crane loads, snow load, and finally the wind load. First, we are going to do that dead load and imposed load values. So this is nothing but the self-weight of the structure can be automatically applied on the robot structural analysis, the software which we are going to use for the warehouse design. Coming to the roof loads, purlin loads we can assume 0.1 kN per meter square or 10 kg per meter square. Roof cladding it is 30 kg per meter square. Building services like finishes we can consider 15 kg per meter square. So all the unit are converted into kilonewton per meter square. So in total we are getting 0.55 kilonewton per meter square. And cooling water pipe and duct system, HVC duct system is required for the warehouse. We need to consider this. For that we can consider 0.35 kN per meter, that is 35 kg per meter. Next one is maintenance category. We need to consider 1 kilonewton per meter square. We have considered there is no major equipment or any major access to the roof system, as it is a sloped one. We can consider the nominal 1 kilonewton per meter square. This is as per European standard. In the right hand side you can see EN 1991 part 1 section 1. In that page number 31 if you refer. So here is category H is given. So category H is given as a roof not accessible except for normal maintenance and repair. So we are considering this H category. So for the H category, the values we can able to find out from here in the table 6.10. So QK, small QK we are going to consider, that is imposed load which we are going to consider. So here it is mentioned that H value can be ranging from 0 to 1 kilonewton per meter square. So we are considering the maximum on 1 kilonewton per meter square. Sometimes this can be reduced to 0.4 kilonewton per meter square also, if it depends upon the accessibility. So we are considering just for maintenance, some equipment may be there with maintenance and repair work persons, so that we can consider the maximum 1 kilonewton per meter square. Next one is coming to the wall loads. So wall loads here we are going to consider the side rail as 10 kg per meter square, and wall cladding is again it is a 30 kg per meter square, which we have considered for roof cladding. Same things we are going to consider. So this is the maximum weight we are considering that, but there are some still reduction in that. So totally it is 0.4 kilonewton per meter square of wall load is going to apply on the column. And coming to the rolling shutter, we have already assumed the 6 meter by 6 meter, that is width and depth of the rolling shutter. So considering it is 15 kg per meter square, that is 0.15 kilonewton per meter square, and weight per meter is nothing but we are going to multiply this 0.15 with the 6 meter deep, so that we are getting 0.9 kilonewton per meter. Also this there will be some eccentricity from the center line of the beam to the edge of the self height of the rolling shutter, the CG of the rolling shutter. So we are considering that as 300 mm, 0.3 meter, in order to calculate the moment due to eccentricity of the rolling shutter. So multiplying that we are getting 1.62 kilonewton meter. So this value we are going to apply on the beam which is to be hold the rolling shutter. And coming to the ground floor level, so there are two type of loads we are going to consider. One is dead load and imposed load. However, in the wall loads there is no imposed load. So for dead loads we are going to consider the floor weight. We are going to provide the floor of 250 mm thickness. So we are multiplying that with the concrete density 25 kilonewton per meter square. So we are getting 6.25. Next one is the imposed load on all the floors. So for that we are going to consider the equipment loads for category E1. For that we need to refer table 6.4 of BSN 1991 part 1 section 1. So here on the right hand side you can see that category E1 in the table 6.4 you can see QK is 7.5 kilonewton per meter square. So that is what considered here. So this category also explained here areas susceptible to accumulate of goods including access areas, areas of storage use including storage of books and other documents. So this is what mentioned here. So the same load we are going to consider on the floors. So next coming to the crane loads. So the crane loads are considered as moving loads. So we are considering the 6-ton capacity of the load, which is 60 kilonewton. So this is going to applied on the two side because we are having two crane beams running on both side, left and right, which we have seen in our model in our previous video. So that 50% of load we are going to consider on one side, that is 30 kilonewton at every 500 mm distance. This 30 kilonewton, that is 3 ton, is going to apply in the moving spacing of 1 meter interval, considering in robot analysis. So this crane load we are going to apply in robot structural analysis tools directly. So two load cases, one moving left and another moving in right side, are we are going to consider for each. So this we will be looking into the detail in robot structural analysis. So for calculating the snow load, these are the main parameters which we required. One is building height, which we already considered during the modeling, is 12.8 meter, that is a height from the floor to the ridge. Second one is a building length is 30 meter, building width is 18 meter, and building height to eaves from the floor is 12 meter, which we have already done in the modeling. And the roof pitch angle is 5 degree, as we are having a 12 meter to 12.8 meter as a height difference. So it means that 0.8 meter is a height difference for the 18 meter, that is half of 18 meter will be a 9 meter. So if you are applying the tan inverse formula equation, that is tan inverse of 8 meter, sorry 0.8 meter, which is a difference between this 12.8 and 12 meter, divided by the half of the width, building width 9 meter. So this will give you the 5 degree of slope. Next one is this zone factor. Zone factor to be assumed as per the conditions, the locations of the project are as defined in the technical specification. In the right hand side you can see that BSNA, that is National Annexer of European Standard EN 1991 part 1 section 3. So here there are 6 number of zones. So we have considered zone number as 3. So whereas our location is fall under this dotted portion, we are just assuming that. So our snow load at ground snow intensity is 0.5 for the zone 3. So that is what considered here. So in order to calculate the uniform snow load on the roof characteristic value, we are having a two formula. So here in the screen you can see that this equation is as per the national annexure. Sk equal to 0.15 plus 0.z plus 0.5. Here that A is a altitude. So altitude which we are having a less than the 100 meter. So if we are applying this in these equations, definitely this value will come less when compared to the general equation which is provided in the 1991 1.3. So the general equation is like S equal to Ui into C mu I into Ce into Ct into Sk. So we are going to apply in this equation the mu one value we can find out in table 5.2. so we can see here it is a mu value is 0.8 here, so we have entered the 0.8 here. And for CT and CE, the CT value it is given directly as 1. Thermal coefficient for thermal transmittance is having a 1, and for CE we are going to consider as per this table 5.1 for the normal case, which we have assumed as 1. Applying all this value here, and we are getting S value as 0.4, and we are also consider the half of the snow, which is 0.2, just 50% we are considering. This is we are going to apply during the load applications and the rope also. So for this wind load calculation, we already released one video explaining the wind load calculations in European standard. So in order to reduce the time wind velocity to the peak velocity pressures, this explanation already provided in the video. The video link is provided in the description. You can find out and learn how to calculate the peak velocity pressure. Coming to the next step, we need to find out the external and internal wind pressure on vertical walls and roofs. So for that we need this input according to the European standard EN 1991 part 1 section 4. In the right hand side you can see that the PDF file which is showing BSEN 1991 part 1 section 4. In that table 7.1 is the external pressure coefficient for vertical walls of rectangular plan buildings. So this is what we are going to consider for our calculations. But however, if you are looking to that each national annexure, suppose we are doing for British UK national annexure, we need to refer this BSE on 1991 part 1 section 4 of national annexure. So in this the table is provided like this. Table NA.4 is to be referred. Both the values are same only, there is no difference in that. So here there are two parameters is given, CPE10 and CPE1. So CPE is, we already know that it is a external pressure coefficient, but here in the national annexure it is provided CPE10 and CPE1 as the same value, but in general European code it is classified in two types, 1.2 for CPE10 and 1.4 is for CPE1. Why this difference is? CPE1 is nothing but it is a local wind pressure for the local members, like it is a single member in overall a building. If you are going to apply the wind load on a single member or any sum of the member which is having a less than 1 meter square of the projected or exposed wind exposed area, then we need to consider this CPE1. In our case we are going to design the whole warehouse structure design, warehouse building, so we need to consider only the CPE10 values. As per this A, B, C, D, E is nothing but it is a area or the projected width of the building. So we will be looking into that. So in order to calculate this coefficient, we need this H by D. H by D is nothing but the height to width ratio. Similar, like if the wind acting in other directions, we need to calculate the H by D in terms of H by L. So that was mentioned here in this Excel, height to length. So similar, like we need to calculate these two, height divided by width and height divided by length. So as we know that height means we need to consider the maximum height, that is up to the ridge. 12.8 divided by 18 is one factor, we will be getting that, and 12.8 divided by 30 we are getting another value H by L. So this we are going to apply in wind on 0 and wind on 90 respectively. So external wind pressure is nothing but WEP equal to QP into CPE. QP we already calculated here in this line 1.1, and we need to calculate this CPE. So next we need to find out the roof types according to that external pressure coefficients. So here that this case is applicable for flat roofs. Our case is not the flat roofs. It is a sloped pitch. And this part is telling that it is a mono pitch roofs. But our case it is not a mono pitch, it is a duo pitch. So this also we can skip it. And here you can see that duo pitch roofs. So from this part we need to find out our external wind pressure coefficients. So here you can have, there are two number of duo pitch roofs. One is pitch angle positive, another one is pitch angle negative. So this case is applicable to for us. So understanding the wind acting direction and the acting pressure coefficient and suction pressure coefficient is very important. So what we are going to do is here in the left hand side Excel you can see that case 1 wind acting towards long wall, that is 0 degree wind we are considering. So this is matching exactly this picture which is showing in the right hand side PDF. So it means the wind is acting in this direction. What it will impact is here in this portion, the longer span of the building will have subject to the external coefficients or external wind pressure which is acting in this phase, and this will go and this wind will exceed in other direction, so that this side the wind impact will be like suction. This acting towards the phase is called as a positive or acting wind or active pressure, and also this side the same suction pressure will occur. Also this side also the same conditions. So this is a first case. The wind, if it is acting in 0 degree, then all the other direction will be in pulling direction, that is a suction, and only in this wind acting phase alone will subject to the active pressure. Similar like if the wind is blowing from here, so this is a next case, then this side it will like suction, and this side also it will be like suction, and this will also like suction. Suction is nothing but if the external pressure is acting away or the pull the structure face, then it can be called it as a suction. And in the third case, if suppose the wind is acting in these directions, that is minus 0 degree or 180 degree, which is the right hand side of the longer span of the building, then again this opposite side will be subjected to suction, and this smaller width also subjected to suction. So this is a concept. So when there is a wind is acting these directions, then all other three direction will be subjected to suction. The wind acting direction will subjected to the active wind pressure coefficient. And finally the fourth case is if the wind is acting in this width, this side will be a suction, all other three direction will be suction. So this is a general phenomena of the wind. So we are going to analyze in all these four cases. Now you can see that E value we need to calculate E equal to B or 2H, whichever is smaller. So that was considered here. So the same equations we are following here. So minimum of length and 2 into H we have considered here. In case E is greater than D, so E we have calculated as 25.6, whereas D is 18 meter sections of duo pitch. So in this E is greater than D, so this case we need to consider. So in this case the picture applicable is A and B only. So that's why in our Excel calculation it is showing minus value here. It means this is the entire width is having the 25.6, as we are going to consider the E value here, but that is greater than the D value. So that's why it is having a minus value, but it is not a problem in these calculations. So from E to that A phase is nothing but E divided by 5. So that was applied here. 25.6 divided by 5 is 5.12. That is a phase. And the remaining all parts, that is 25.6 minus 5.12 is a 20.48 is a remaining part. So the A and B is applicable for this case. So this picture will explain this. So this is the text A to E means it is the external pressure coefficient phases in terms of vertical, that is the wall claddings. So coming to page number 45 for DO pitch roof, you can see that F2I. So this notation F2I is means for it is for a roof pitch, rich or rough. So all this we need to calculate. So we need to calculate the external coefficient for various phases from A to I. A to E is a wall cladding and F to I is for roof cladding. So also we have calculated the H by D, that is H is a total height 12.8 meter divided by D is width is coming 0.71. So according to that we need to find out the calculations. So these are the roof area we have calculated here. So according to that E by 4 is a, so here you can see that E by 4 is F phase and G is a remaining phase. So E by 4 is nothing but we have calculated the 25.6 as E here. So that divided by 4 is coming 6.4. So these are the F phase distance, and the remaining, that is 25.6 minus 6.4, 6.4 will be 7.2. So that phase is going to apply on the G, and remaining H, J, I are having the length of 30 meter, overall length of the building. And similar like 2.56 in this direction is it is showing as E divided by 10, that is 25.6 divided by 10, and J also the same value, E divided by 10, 2.56. So remaining things we need to consider as 6.4. So this is what the explanation of roof panel divisions according to that picture showing in the right hand side of EN 1991 part 1 section 4. So now we are calculating that F, G, H, I, J values, so which is having a width. So F is having 2 numbers and G is having 1 number of panels. H, I, J are also having a 1 number of panel. So we are applying this area calculations. So 6.4 into 2.56 will be having 16.38, and for G sections 17.2 into 2.56 is 44.03. So likewise we need to calculate all the E, F, G, H, I, J panels. So total we are getting 539.99 meter square as the exposed area. When coming to that wall side, that is A, B, C, D, E, so we need to find out the coefficient factors. So for that we need to go to page number 39. So this table is extracted in this Excel. So you can see this is as per national annexure. So national annexures we have seen here. So as per this national annexure value, we have considered here the extracted value of this. So up to here for wall cladding phases A to E is maintained here, and similar like for the roof cladding, that is F to I, F to J, you can see here in the left hand side Excel sheet for that page number 25 of that national annexure BSCN 1991 part 1 section 4 to be referred. So here you can see that NA7A shows, the table shows external pressure coefficient for DO pitch. So this value also extracted in this Excel, so that our calculation will be very easy. So here what we have considered is for H by D, we already calculated this in both the direction. So that factor is what there. And for this roof zones, the roof zone to be calculated as per the pitch slope, 5 degree Celsius, 5 degree slope is ours. So accordingly these values are extracted from that table. So for A portion it is subjected to 1.2, 0.8, 0.5, 0.46 directly generated, and similar like for roof cladding also this is extracted from this table according to the slope 5 degree. So this external pressure is directly calculated from this 1.2 into 1.11 kilonewton per square meter. So this is simply multiplication of CPE into QP. Similar like for case number 2 also we need to calculate in such a way. So here wind is acting 90 degree. So the same method we are going to follow, but the direction is differing. So that wind direction according to that, so this is a wind direction. So here that E divided by F will be coming in this direction. So same kind of calculations, and this pressure coefficient used to pick from the tables here listed. So these are the other cases. The wind is acting in right hand side of the longer span. This is another case. So these are the way which we are calculating the external wind pressure coefficients. And coming to the internal wind pressure coefficient can be calculated based upon the figure 7.13 of BSCN 1991 part 1 section 4 53. So it is mentioned that if the openings is 30% more than that, then we need to follow that 7.3 and 7.4. So for that we need to check our openings. So here that we know that shorter direction openings are like there are 3 doors we are having. One is first one is a rolling shutter of 6 by 6 meter, and other 2 are 2 by 2 meter wide and 3 meter height of doors. So applying this we are getting 48 square meter, and we know that the cross area, the exposed face is 18 by 12 meter, that is the width and the height up to you. Opening ratio is giving only 22%, which is less than the 30%, so you can follow the conventional method. And this method, you can see this chart, we need to find out the HPT. H is the height, total height 12.6 meter, which we have assigned here as a height, and the D is the 18 meter. So H divided by 18 is coming 0.71. So from this graph, if we are going to draw for the mu value is 0.33 is the least one, but in our case we are getting only 0.22. So we can skip this graph also. We can directly consider these no two values, which is stating that internal pressure can be 0.2 positive and minus 0.3. So that is why we have considered here in this Excel sheet. So this we can eliminate, and this is the thing we need to follow. So 0.2 is the internal pressure positive, and the negative acting inwards 0.33 and 0.22 respectively. So now we are going to create the external wind pressure summary. So as we know that there are 4 sides in the building. So windward face is nothing but, if you see in this page number 45, the image is well explained. 46. So this direction is a windward. You can consider this as a A. So leeward is opposite to the wind direction. So that is 0.47, and side face is both the side face. We need to consider 1.15. So how this is arrived is, so this is directly calculated in the first case, that is wind in longitudinal direction from the left. So it is a D 0.84. So in this picture we can see D is the wind facing elevation and E is the exit. So here, as it is a section, it is in minus value. We are considering that. Similar like side, we are considering the maximum value of all the three. So which is 1.3. A, B, C is nothing but the side view you can see here with the direction. So this is applicable for both the sides, and the roof. For the roof, windward, leeward are there. So in this picture you can see that half of the portion is called as windward, and the right hand side half portion is called as leeward. So likely that E, F, G, H are falls under windward, and E, F, G, H, and J, I are falls in leeward. So that is why multiply here and find the maximum external pressure 0.94, and the downwind, that is leeward side, is also calculated as for I and J. So this is what done here. So this is a summary for case 1, that is wind acting in left hand side of the longer wall. Second case is wind acting short side, that is in the rolling shutter side from the top, which is here in the case number 2, wind acting in 90 degree. So the D to be considered here. So here side face is a longitudinal wall, so A, B, C to be considered, and the leeward face is E. So in this picture you can see wind is acting in this direction. So this is D, this is E. So this picture showing wrongly, here is E, but we should come here. Similarly for wind acting towards the long wall in the right hand side, so this is what the same philosophy we are applying for this case 3. And case 4 is a wind acting size, which is from the bottom. So this is all the summary of 4 cases. Look description for more related videos and subscribe to this channel for more updates. Thank you.